So feel free to still ask questions as we're going by typing in the chat. And if you're dying to unmute, of course, you're welcome to do that too. I just know sometimes you guys hate unmuting. Okay, so moving on here. The jump start is reminding us about this thing called interval notation. Interval notation. And so right here, they're giving us some intervals to talk about some different graphs. So let's take a couple of notes about this real quick in case we don't remember. What the heck is interval notation? Okay. I'm just writing this up at the top blank space of your page. So interval notation is a boundary set on the x-axis given to us in values with little parentheses. So for example, in Jumpstart Part A, it says that the interval is from -2 to 3. That means that my boundary is a graph that goes from x equals -2 to x equals 3. So all this is saying when I read this is I say to myself from -2 to 3. That is interval notation. Anybody want to try typing what this means? What does this one mean? If the other one was -2 to 3, what would this interval be? Type it in the chat for us. From what to what? Okay, awesome, Maya. This one means from. Now, notice how Maya just simply said from 2 to 4. I'm actually writing a little bit extra from x equals 2 to x equals 4, but you can absolutely just say it simply like Maya did from 2 to 4. Okay, I want everyone to try part C, writing out that interval notation for me. From what to what? Everybody take a minute. How would I say that interval? You're writing this in your packet on page 43. Okay, nice. Hopefully you match what Jonathan put. We're going to say from 0 to 2 or from x equals 0 to x equals 2. Now, there's one other thing I want to mention that you guys may or may not remember, and it's about the brackets. Okay, there's something about the brackets. The brackets matter in interval notation. Recall that an open bracket is drawn as parentheses. Okay, open brackets are drawn as parentheses. And what do open brackets mean? They mean not included. So if I said that my interval was from -infinity to 3 and I used open brackets, I always use open brackets on infinity because I can't touch that point. Infinity goes forever. But what does a 3 open bracket mean? It means that my graph goes all the way up into 3, but does not include 3. My graph does not touch at 3. So it's sometimes, if you guys remember, there's like an open dot at 3. So we use open brackets to mean not included. Go ahead and write that down. What's the last one we're going to review? It's called closed brackets. And they're these ones that kind of have little corners. They're like the same thing. They're like parentheses, but with corners. Closed brackets mean that the values are included on the interval. And all of the examples you just read to me, do you guys see how those all have closed brackets? So when it said interval from -2 to 3, it includes the -2 and the 3 and all the numbers in between. This one includes the 0 and the 2 and all numbers in between. This one includes the 2 and the 4 and all numbers in between. Type in the chat if you remember the brackets about open brackets and closed. Type in the chat, don't remember, if you don't remember the brackets. Yes, you remember about brackets, or no, you don't, because this helps me for tomorrow's lesson. Okay. All right, let's go down now. Thank you for sharing that, you guys, that most of us don't remember. Look at the chat, so you're not alone. Most of us don't remember. So that's what Ms. Sanchez is going to be doing tomorrow. Now, by the way, notice how a couple people keep getting kicked out of Wi-Fi. If they can just watch, if they're at your table and they can just watch on your computer, that'll lower everybody's stress level. So if you want to share and watch on someone else's computer, feel free to do that. Okay, today we're going to be comparing a quadratic and an exponential function. We're going to be determining which type of function it is, which one grows faster, and how does the growth of a quadratic compare to the growth of an exponential. So remember that our quadratic is our new U-shaped graph, and our exponential is a curve. So we're going to be talking about the comparison between the two in this tortoise and the hare situation. So in the children's story of the tortoise and the hare mocks the tortoise for being slow. The tortoise replies, "Slow and steady wins the race." And the hare says, "Well, we'll see about that." The starting line, the hare, is given this function. So everybody put a little comment on the side. The hare is our d equals t squared function, where d is in meters and t is in seconds. But because the hare is so confident that they can beat the tortoise, he gives the tortoise a 1 meter head start. Oh, look at him being all like, oh, go ahead, take a meter head start. The distance from the starting line for the tortoise is d equals 2t. So for this one, I'm going to make this our purple function, and this is the tortoise. Okay, so at what time does the hare catch up to the tortoise? I'd like you guys to take a second to make me a quick table. Okay, in this table at the top, we're going to have the time in seconds. Sorry, guys. I keep grabbing the wrong thing. Okay, that and then that. And then we're going to be looking at these two different functions. The red function was our t squared. And then the purple function is our 2 to the power of t. Okay. So across the top, let's keep that going. How many seconds have passed? 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, and 5. When you have your table ready, can you type ready in the chat so I know you're ready to start building it? Take a minute to get that table ready. Tell me when you're ready. Check with your neighbor, see if they have any questions. Okay, so what does this mean? It means I'm going to take all of these inputs. I'm going to take this 0 and I'm going to plug it in for t. For example, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. So I'm plugging in the inputs to get an output. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on and so forth. I'm plugging in to my function to get the output. Well, you could grab a calculator to do these, but you probably trust me. So 2 to the power of 0, or anything to the power of 0, is just 1. 2 to the power of 1 is just 2. 2 to the power of 2. 2 to the power of 3. 2 to the power of 4. 2 to the power of 5. There's all my outputs for the tortoise's function. Now do you see what they meant by giving him a head start? He's already 1 meter ahead at time 0. And if you wanted, you could plug these all into a calculator to see how I got these answers. But did you see that this is just times 2 exponential function? Okay, so we filled out the bottom of our table. Now we're going to fill out the t squared part. Plugging in 0. What would 0 squared be? What would 1 squared be? What would 2 squared be? Is there a student that's willing to fill this in for me? Take a minute to fill it in. Will you read me what you got or type it in the chat? What would 0 squared be? 1 squared. 2 squared. Okay, so Jonathan's saying 0 squared would be 0. 1 squared would be 1. 2 squared is going to be 4. What's 3 squared, you guys? Nice, Ruby. What's 4 squared? Nice. And what's 5 squared? Nice. Okay, so now we've got these two functions, and they asked me, when did the tortoise catch up? I'm sorry, when does the hare catch up to the tortoise? Type in the chat, where do you see that they caught up to each other? Where are they the same distance? Nice, Valerie. Nice, Natalia. Okay, great. Do you guys see this right here that they're noticing? They're both at time 4. So here's how we write this. We would say at 2 seconds, they are both 4 meters into the race. At 2 seconds, they are both 4 meters into the race. They are tied. They are caught up. All right. Once you have number 1's table and sentence done, please type ready in the chat when you're ready for me to go to number 2. Go down and start looking at number 2. If the race course is very long, who do you think wins? Type ready in the chat when you've got your table and your sentence done. Christian, Jalord just got kicked out. Can he look onto your computer if his computer's not working? Thank you. Okay, this full key is going to be attached in case you guys need it later. So if some of that went too fast for you, you can copy from a neighbor or you can see the key later. Okay, if the race course is very long, who wins? Type in the chat. Do you think the tortoise is going to win if the race is very long, or the hare? Remember that our tortoise is t squared and the hare is 2 to the t. What do you think wins in the long run? All right, we've got a lot of votes for the tortoise. Nobody's going for the hare. Nobody thinks the faster hare is going to win. Okay, let's actually take a peek at the graph overall and see who's right. You guys do not need to pull up Desmos. I'm going to pull it up for you, and I'm going to put the little graph into there. Okay, so we've got two functions. We've got the t squared function, and we've got 2 to the power of t. I'm going to call it 2 to the power of x. And so check this out. All right, so right here is where they tied. Do you guys see that? This is at 2, 4. That's where they tied. So this red one is the hare. And then it catches up to the tortoise, but whoa, what's going on here? The hare is winning, the hare is winning, the hare is winning, the hare is winning, and then boom, something happens right there again. The tortoise takes over. Those of you that said the tortoise, you were right. Let me go ahead and screenshot this to get this into our, if you said tortoise, you are the winner. I want to screenshot this whole thing in there so you guys have access to it. Hang on. Okay, so let's put this down in full writing. We would say at the beginning, the tortoise starts out ahead because of the head start, right? Until what point? Right at time 2, until 2 seconds. Then the hare caught up and starts winning. Okay, so that's this segment right here in the middle where the red line's over the blue line. But then what happens right there at 4:16, you guys called it, but at 4 seconds, maybe the hare gets tired. The tortoise takes the lead again. Okay, so you guys can write this in your own words. You don't have to be writing it exactly how I put it, but you get the gist of it. That first the tortoise is winning, then the hare catches up, then the hare is winning until 4 seconds, and then the tortoise takes the lead again forever and after, okay? So at what times are they tied? We've now got 2 spots. Okay, so the 2 times they're tied. You guys already noticed the 2-4, but now we saw in the graph that there's also another tie. They're at the exact same spot at 4:16. So these are the 2 times that they're tied at 2 seconds or 4 meters, at 4 seconds and 16 meters. Okay, question for you. If the race is only 15 meters long, who wins, the tortoise or the hare? So looking at this picture, at 16 is where the tortoise starts to win again. So going back to 15, who would have been winning then? You got it, Ruby. If the race is only 15 meters, the hare would win. In fact, the hare would win anytime between 4 and 15. That's my interval notation. Between 4 and 15, the hare's the winner. There's Chelsea, the big dog, not the puppies. So between 4, technically, let's do this. They're tied at 4 and 16, so we can't include those. Anywhere between 4 and 16, like 15's in between, the hare would win. Okay, let's put this in table format to make sure we understand. On the first interval, the tortoise is faster. They have the faster rate of change. But then between 2 and 4, the hare is faster. And then from 4 on, the tortoise steals and is ahead again. Okay, take a minute to let me know when you've got all of these written down. Does anybody need me to go back any, or can you copy from a neighbor? Let me know when you've gotten all the way down to number 5. You can say done or ready when you're ready. Thank you, Maya. Okay, for the next one, y equals 2x squared and y equals 2 to the x. Decide which function grows faster for large values of x and explain why. So I'm going to go back into my Desmos. Actually, first, let me just insert the other one. So I'm going to go up to Insert Media. Remember that you guys don't have to have this. I'm putting it on the digital key. And so it will be on my key online. You don't have to have it. So there's the graph that supported all of our thinking on the one before. Okay, so now let's go look at 2x squared. What if I throw a 2 in right here? Is it still going to be the case? Whoa. Okay. So if this was the case, let's see where they intersect. Okay, it's not a pretty intersection on that one. So if this was the case, which one grows faster over time? Still, the exponential function will beat it out eventually. See how the blue one eventually takes over the red again. Okay. So if y is equal to 2x squared, the exponential curve will still beat out the quadratic in the long run. It's just going to take longer if it's a 2x squared. It's not going to happen at time 4. It's going to happen a little bit later. But the exponential, what's the story here? The exponential is always going to beat out the quadratic in the long run. And that's the power of exponential growth. It beats out linear and it beats out quadratic. Okay, what are our takeaways? I know Maya likes to fill in all the blanks on these pages. So you guys can feel free to draw the sketch, the shape of the graph. Your quadratic function was going up in a curve, and your exponential function was going up also in a curve, where it crossed over like this. And so there were 2 places where they were tied, and it ended up beating out the quadratic. Okay, so if you wanted, you're able to sketch the graph, but what did I do? I just did the media digitally this time, and I pasted it in. Okay. What were the 2 equations? We had the t squared equation, or x squared, and we had the 2 to the power of t, which we called 2 to the power of x, because Desmos likes x's instead of t's. What was our table? You could say C number 1 on the task. We made a table for this. And the rate of change, if you guys look up here, rate of change was number 5, talking about which one was faster. So you could say C number 5. But our big takeaway is that the rate of change of an exponential will always surpass the quadratic. Okay. Now, it says that right there under lesson summary in different words. So you don't even need to write this takeaway down if you don't want to. You could just highlight right here what this is saying. Okay. When you are ready to go to the ready, can you type ready in the chat? When you're ready to move on to the next page, remember that you don't have to do a graph. I did it digitally here on the task. Okay. Now, I'm going to do the retrieval starting on page 47. Remember that the retrieval is like the warm-up to the homework. It's the warm-up to the ready and the go. And then we're going to get through almost all, if not all, of the ready and the go together. After we do the ready and the go together, if we finish it all, you have no homework. If you don't finish any of this, feel free to go back to the video. What are we skipping? We are skipping the set. Okay, a couple of notes from Math 1. How to tell if something is a function or not. Function or not a function. Okay, let's see if you guys remember any of this from your math teachers last year or even the year before. How to tell if something's a function. The first rule is you cannot have, the definition is for each x value, there is only one y value. What this means is you cannot have any repeating x values in a table. Awesome, Ruby. Yes. Oh my gosh, Jacob, awesome. So for every one input, there's only one output. For every one x value, there's only one y value. For every domain, there's only one range. So let's go take a peek at the first number 1 on the retrieval. It's giving me x and y values. I'm going to go highlight the x's because telling whether it's a function or not, it has to do with the x's. So highlight those. And do I have any repeats? Because I cannot have any repeating x values. If I have repeating x values, it's not a function. Maya, which one is repeating? Yes. X equals 3 repeats. So that means no, it is not a function. So that's kind of an easy one. We just look at the values. We look to see if there's any repeats. Do you see how there was an x equals 3 here and here? So we say, no, it's not a function. Okay, now let's look at a graph. And I want to know if you remember the thing called the vertical line. Yes, Jonathan, the vertical line test. When we do the vertical line test, how do we know for every one x there's only one y? It can only touch once for it to be a function. So let's go do the vertical line test. You're going to just draw with your pencil straight down on the picture. You're going to go like this. Vertical line, touches once, touches once, touches once, touches once. If I can only touch once anywhere I draw that line, guess what? Yes, it's a function. Okay, can you guys go down and do the vertical line test on numbers 3 and 4 and tell me what you think? Are they yes, they're a function? Do they only touch once? Or are they no, they're not a function? Touches once, touches once, touches once, touches once, touches once. Vertical, 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 vertical. Excellent job, Jacob. Excellent job, Justine. These are both, yes, they are a function. Perfect. Okay, that was the warm up to the homework. Now your homework is going to be, oh, sorry. I almost forgot this other part. It also wants us to remember about the domain and range using interval notation. So not just, is it a function, is it not a function, but what's the domain and the range for each? So remember that the domain, let's put a couple notes here. The domain of my function are the x values that make sense. And the range of my function are the y's. Okay, good, Jonathan. I'm glad you brought this up. On number 3, for some students, it's not clear. When our packets do not give us a dot, these are going on forever. Can you guys draw little arrows at the end of that? For sure, draw those arrows. And so like Jonathan said, exactly, Jacob, minimum and maximum values for each axis. Exactly. So to say this first function, number 3, is going to infinity to the left and infinity to the right, I would say that the domain, as Jonathan said, is all real numbers. And the symbol for that, Jonathan, if you recall, it's kind of like an R with a double back. It's all real numbers, something like that, right? But they asked for our answer in interval notation. So we're actually going to say that the domain goes from negative infinity to infinity. Does that make sense, you guys? The domain goes all the way left and all the way right forever. So we're going to say it goes from negative infinity to infinity. Type in the chat if this is starting to come back to you, or you could say totally lost, Ms. Sanchez. I have no idea what domain and range are. Type in the chat. Are you sort of starting to remember this, or are we totally lost? Okay, I've got a little bit of both in this class. In period 1, no one remembered. Okay, for the range is always going to be the minimum of the graph, like the lowest y value, and the maximum of the graph, like the highest y value. So let's go look at these boundary lines. The minimum of my graph, I want to say is right here, but there's a trick. Do you guys see how these arrows go forever? So what does that mean about minimum values of the graph? It means it goes down forever, forever, forever. It means my range goes from negative infinity. It goes down forever. But it definitely has a stopping point at the top. What's that stopping point at the top, you guys? Where does it stop up there? 7. Awesome. So the answers that you're giving me, Jonathan, are correct. You're just not putting them in interval notation. You're putting them in set builder, which is also perfect. But right now, since this is asking for interval, I'm going to keep going back to interval. Beautiful. Okay, let's go look at the next one. The domain of the next graph does not go forever left and forever right. The domain definitely has a starting x value and a stopping x value that are included. So take a minute. Please don't type it in the chat yet, you guys. Let everybody try. Where does this graph go? From the left at what value? What value is this? Don't type it in the chat yet. To the right to what value? From where to where is my domain this time? Give everybody a minute to try it. Okay, now feel free to type it in the chat if you want to try it. Where did you think it went from the left to the right? Okay, very nice, Valerie and Jonathan. From -3, because we go like this. This is my 0. So we go 1, 2, 3. So from -3 to 10, notice the closed brackets that Jacob and Ruby have. Closed brackets because we want to include the -3 and include the 10. Because those values are included, solid dots, Jacob, exactly. Okay, great. Now the range goes from my minimum to my maximum. So the lowest y value on the graph, where's that going to be this time? to the highest y value of the graph. Where's that going to be? Okay, Ruby says from -1 to 4. Do you guys see those values that she just had? Now, I do want to put a little coordinate pair up here so you can understand also where some students like to do this. Does everybody see that this dot back here is at -3, 4? And this dot right here is at 10, -1? Like that's the actual coordinate pair where it's located. So if I were to ask you where's the domain, do you see that the domain is this x value to this x value, and that the range is this value to this value? So some people like to put those coordinate pairs and then just look, domain is the x's and range is the y values. Do you see how those show up in your domain and your range? So writing out those coordinate pairs can be really helpful. Okay, I'm going to pause the video here for a second.